Video, I'm gonna go over the logistic regression model that we developed in today's class. Just as a recap, we were interested in looking at a logistic regression model to predict damage to culverts in Texas. Culverts, as you know, are structures that facilitate the movement of water across bridges, across roads. So there are a variety of different types of structures and culverts, and there are about 20,000 culverts in Texas or more. And the idea is to develop a model to predict the unsatisfactory state of structures of these culverts, or the satisfactory states of these culverts. The Federal Highway Administration looks at rating these structures, and they use a 10-point scale going from 0 all the way to 9. Values about 6, 7, 8, and 9 can be considered as satisfactory in this or better. And then values below that from 0 to 5 can be considered as unsatisfactory and also include imminent failure and failed states. Okay, so we have essentially taken this 10 scale rating and converted it into a 2 scale rating of unsatisfactory and satisfactory, and we want to predict the culvert ratings of satisfactory and unsatisfactory using a logistic regression model or using other predictors. The data for this study was taken from the Federal Highway Administration. I show you the website. This is the 2018 data release, which was updated in 4/22/2019. It was downloaded as a CSV file and cleaned up for you. Previous studies on similar efforts have indicated that for bridges in particular, the ratings of failure or non-failure depend upon the age. Clearly, age is calculated as the inspection date, which would be 2018, to the reconstruction date, which is the year in which the culvert was built. Some researchers have found that adding the square term of the age improves the predictive capabilities of this model, so we're going to add that as well. So the age is basically a very comprehensive surrogate for a variety of things: the load that the structure has experienced, the material characteristics, or the level of deterioration that has occurred in the material that has been used. All can be factored using this age, or like in a model using this age parameter. The average daily traffic per lane, or the ADT, gives us a measure of traffic or the vehicular traffic or the loading on that bridge. People have also found that some of these culverts have been reconstructed, so the reconstruction record binary variable would say is 1 if it has been reconstructed, or 0 if there has been no reconstruction is also a helpful variable. And then the percentage of truck traffic on the culvert could also be could be high, because trucks generally tend to have a higher loads and a measure of much higher loads, and therefore a greater damage potential. So the logistic regression model, we'll use the scikit-learn package, and this package does not actually maximize the log likelihood, but also adds a regularization term. And actually, if you go to the website, it takes a minute here, it does say that the regularization is applied by default. So and then it uses a variety of different penalty terms. We are going to use the L2 penalty, which is very similar to the maximum likelihood, but we have to deal with this regularization term. So there is a inverse of the regularization strength, or a parameter C, and what this C says that is that smaller values of C specify stronger regularization. And as I talked in the class, regularization implies that in addition to minimizing the maximum likelihood. The logistic regression model also tries to minimize the number of model parameters that are needed to set up the model. So with that background, let's go to Python, and I'll quickly go over the code. So what I have up on the top is the code doc, and and essentially it includes basic information about this module, when it was written and what it does and who wrote it. Our second step is to load the libraries. Clearly, we are going to load this OS library because we want to change our working directory. We're going to import pandas because we have a CSV file that you should have as well. And that CSV file is this Texas culvert data that we are going to use. And it's got several attributes. What we are interested in is modeling this culvert damage, which is a binary variable, and we are going to do that using service year, the square of the service year, ADT, whether there has been reconstruction of the bridge or not, as well as the percentage of truck traffic that is on. So we're going to use these four variables, and we're going to add another variable called the square of that age, or the square of that service years, to our model. So so we need to make sure that it is in the working directory that we specify. Again, we can specify a directory, and then we're also going to be using the scikit-learn, which is the sklearn. Sklearn is a very big package. It's got several modules to it, so we don't need to import everything. So from sklearn model selection module, we are going to import the train test split. And this train test split is a function that we can use to split our data set into training and testing data sets. Similarly, from the scikit-learn linear model library module, we are going to import logistic regression. Logistic regression is the class that provides us functions to do logistic regression. From the scikit library, we are also going to import metrics. Metrics helps us evaluate logistic regression by creating contingency tables. We also want to make some plots, namely the plot of the receiver operating characteristics, which is a measure of how well your logistic regression model fits the data. And for that, we're going to use matplotlib library, and especially the pyplot module, which we are going to instantiate as a PLT object. We are also going to bring in Seaborn as SNS. Seaborn is another visualization package, and Seaborn really has some advantages to bringing in Seaborn, even if you're using matplotlib, because it helps clean up the plots, or make those plots made using matplotlib look better and pretty. So our first step is to load all these libraries. So I'm going to select this and then run it, and the model ran fine. It imported all those libraries. The second step to do would be to change my working directory. Here I've created a variable called dir, and once I have done that, I am going to use the OS package and the chdir method that's in that OS package to change my working directory. And if I go here and say os.get current working directory, it should show me that I'm in the directory that I want. Okay, so once we get this, the next step is to read our data set, and to do that we are going to use the pandas library. And the pandas library has this read_CSV, and then this tx culvert data is the file that we're going to read in, and we are going to read that into an object called a. So that's what this function does. This is what this line of code does, and we ran a. As you saw before, that tx culvert data has several attributes which we're not going to be using here. What we're interested in is the SVCR, ADT, reconstruct, and PINIT. These are our input variables, and the culvert damage is our output variable that we are going to model. So what I've created here is a list called features. Features has the column names or the attribute names for the features that I'm going to be using as inputs. So SVCIR, ADT, reconstruct, and PTruck are those 4 variables. So what I'm going to do is I'm going to first create an object called features, and then I'm also going to create another object or a data frame called X, which essentially extracts the feature columns from A. So if I run these 3 lines of code, I've already run the first, line 24. So if I run these 2 lines of code, I am going to pull out the features. Okay, and of course I want to add age square to my model, so I'm going to make that calculation here, and I'm gonna call it SVCYR is basically the service year, or the years of service that culvert has been in place. And again, I'm squaring that, and then I can add this very simply to my existing data frame X, which is the input data frame. So I'm just going to say X of this column. So I want to add this column, and I want to add values to this column. So if you run this, so it basically takes a copy and puts a copy of this data into that column, and it does throw me a warning that says that setting with the copy warning. So essentially it is saying that I've made a copy of and put it into the data frame. Okay. Then I want to take this YA equals culvert damage, and that is our output variable, so I'm going to pull it out separately. So having gotten my data set, my inputs and the outputs as data frames, the next thing I want to do is split this data into training and testing. I'm going to use the training data to train my model, estimate the model parameters, and then I'm going to use the testing data to test the model to see how well the model does. Clearly, the testing data is not being used to develop the model or estimate the parameters of the model, so it provides an independent test of how well my model is performing on data that it has not seen. The train underscore test underscore split data, as you can see, comes from the sklearn model selection library. Since this is the only function we have pulled out, we can use it directly. And the train underscore test underscore split, I want to split my X, which are my input variables. I want to split my Y, which is my output variable. And I want to have 30% of that data in testing mode, and then the remaining 70% is used to train this data set. So quickly, if I go here and do len of X, it tells me that I have 19,951 or close to 20,000 records, 20,000 culverts for which I have the data. And what I want to do is take about 30% of that and then call it a testing, which the model is not going to see, and then the remaining 70% is training, which the model is going to see. It also has this, another specification or another argument called the random underscore state. And what we do is, if you give this random underscore state, it's always going to use this value as a seed to start your random number generation or random number shuffling. So if you want to reproduce your data, put random underscore state and give some value to it. Of course, if there is no value to it, it'll randomly shuffle data each time, and you will get slightly different results when you make multiple runs. So if you want reproducibility, you keep this. If you don't want reproducibility, you remove it. Either way, for the fairly large data set like this, I don't think the differences are going to be very significant. So then what we do is, clearly we are storing training data, testing data, training data, and the testing data for the output. Notice I've used capital X for train and capital X for test, and then y underscore train and y underscore test for the lowercase y's for my predictors, like an output variables. So I want to instantiate the model using default parameters for most part. However, I do want to change the value of this regularization and make it a fairly large number. Remember that 1 over c is what's used as the regularization parameter, or the weight for that regularization parameter in that objective function. So by making c very large, I'm essentially saying I just want to do L2. I really don't want to do any regularization on my estimation procedure. So that's your log reg, and that's your logistic regression. So if I run this line, that line will give me the splits of my data. So I have X train and Y train, as well as X test and Y test, which is about 30% of the data. So first I instantiate an object. So this is the object I'm instantiating. This is just saying that I'm going to create a model object called logreg, which belongs to the logistic regression, and it's going to use most default parameters for, but the regularization parameter is going to be different. Once we get this, I can use the logreg.fit function that is associated with this logreg object. The logreg is the logistic regression object, and I give my X train and Y train and make sure that your caps are given correctly. And basically the model runs and tells us that the default solver will be changed in the next version. But really it's just a future warning. We don't have to worry about it. So we've fitted the model. So our model fitting part is done. Now what we want to do is essentially use this to test the data. So if I want to make predictions, I can use logreg.predict x.test. So if I just run this like this, it runs. And then if I go here into the console and put y underscore predict, y underscore pred, what you are seeing is, sorry, I'll just rerun this. I thought I had run this. Lowercase, y underscore, and then lowercase pred. And you will see an array of zeros and ones. So you're not seeing any ones here because it's not showing all the data set, but I know there are ones because I can just add up. And I know that there are 2040 ones, and then len of y underscore pred, there are 5986 records, of which about 2040 are ones, are predicted as ones, and the remaining are predicted as zeros. The 0, remember, is satisfactory. 1 is unsatisfactory in our case. And if you look at the Culver data, so when I have my basically 8 or 7 are goods, so I have zeros, and anything below 7, 6 or above, will get a 1. So unsatisfactory states are 1, satisfactory states are 0, and it's predicting some cases to have satisfactory states and some states to have unsatisfactory states. Typically in a logistic regression, we don't get a classified information like this. What we get are probabilities. So if I run this line, and instead of doing a predict, if I say predict the probability A, so I can store that in yprob. And if I do yprob, you can see that it's giving me 2 sets of probabilities. This is the probability of getting 0. This is the probability of getting 1. And of course, you can convert this into a data frame and then write it into a CSV file so that you can take and look at these probabilities and do other types of analysis, maybe in another language like R or someplace like that, or come back to it and write some other new code with it. So this is how you pull out the output of the model. You can also get the parameters of the model. These are the definitions that have been used. Like we said there are 100 iterations. We're going to use the L2 penalty. This is the tolerance for convergence, and then the C parameter, of course, which I've varied. If you want to pull out the coefficients, and these are the coefficients, so you can pull them out and notice that your x dot, let me try this. We can look at x dot head and notice that the service years, ADT, reconstruct, ptruck, and service year 2 are essential parameters. So if I take this and run it, so the first value here corresponds to this value here. The second value here corresponds to reconstruction. The third value here corresponds to ptruck. So the service, this is the first value goes to the age, the second value goes to ADT, third value goes to reconstruct, fourth value goes to ptruck, and the fifth value goes to the square of that age, or age squared. Okay, so those are your coefficients, and of course your model also has an intercept, so you can run that and you get the intercept value as well. So using this, you can write your logit model. You can also write the probability model of y being unsatisfactory or y being satisfactory from that logit. The way we usually evaluate our models are by using confusion matrix, and to give you a glimpse of that confusion matrix, what it is we have a predicted class here, we have the actual class here, and there are two categories which are called cat and non-cat. And if the actual class, if the observation is of the cat category and my prediction is also of the same, I get true positives. So, and similarly, if it's non-cat and non-cat, I get true negatives. And of course, so the diagonal elements are the correct predictions by the model, and the cross diagonal elements are wrong predictions by the model. So we want to make sure that these two numbers should be significantly larger than these two numbers, because that would mean that the model is predicting overall, making better predictions than wrong predictions. So we can define a variety of different metrics, and again, you can go to the Google page, Wikipedia page, and there is also and this is based out of a paper written by Fawcett on ROC analysis way back in 2005. So it's got a variety of different formulas. In addition, the sensitivity, the specificity. The sensitivity basically tells the true positives, that is, how many times has the model predicted positives correctly of all the positives that were observed. Similarly, true negatives tells us the number of times the model has predicted the negatives or zero values correctly of all the observed predictions. Okay, so that's how we get these true positives and true negatives, and then So remember that the model has predicted some false negatives and false positives as well, which means the model has some errors in its prediction. So we can use this true positive, and again, these are called sensitivity, recall, and the true negative rate is called specificity, or selectivity, so on and so forth. We can define a variety of different contingency measures, and I urge you to go through this at your leisure. So we first create that confusion matrix, and to create that confusion matrix, we are going to use the sklearn also has this metrics module, so we can pull the metrics module, we can run it, and it creates a contingency table. Basically what it's telling us is that our model is predicting 2716 correct values, like zeros when satisfactory states, and 1251 non-satisfactory states, if you may. And one way to do that would be to say sum of y pred, sum of, and I think I called it y underscore pred, and that's 2040. Okay, so if I take 1251 plus 789, which are these two numbers, I should get 2040. So this is the model predicting. So the model is on this axis and the observed are on this axis. And if you notice, when we did y test, the x-axis is here, so it places the first one as rows and the second one as columns. So that's what this model does. So model is basically, since you gave the testing, it will put the rows as testing, and then it'll put the columns as prediction. So these are your predictions of 0 and 1. These are your observations of 0 and 1. Okay. And then I can just add a comment here and say y underscore test is going to be rows which are observed, and then y underscore pred, which is predicted, are columns. Okay, so we got our confusion matrix, and we can use this confusion matrix or also we can use the metrics to get your accuracy score. Again, we are giving testing and prediction for all of this, and my accuracy is about 66.2. So there is 66% accuracy. Remember, I'm doing this on testing data, or the data that the model has not seen. So this is a fairly good number, especially for a data set that is a large data set like the ones we have with considerable amount of variability. Okay, and the precision, it tells us that there is a 61% precision. Okay, so if we go back to our precision is basically saying the true positives over true positives and false positives. So how precisely true positives and false positives are your zeros, if you may, and if you say how many times have you gotten your positive prediction, which is the prediction of unsatisfactoriness, correctly over everything that's in the observation. So our model is doing pretty well. It's doing about 61% of the time, but it does even the accuracy, which includes both the 0 and 1 predictions being correct, is on the higher side. It's about 66%. Okay. Similarly, recall is the opposite version of it. So if you look at recall, it's about 50%. So the model does good. This is overall accuracy. This is predicting zeros, and this is predicting 1. Okay. So it doesn't. So it predicts as satisfactory well, better than it predicts unsatisfactory states. I talked about ROC, and ROC is another way to look at your models. So the receiver operating characters essentially plots sensitivity and 1 minus specificity here. So this is the true positive rate, and this is a measure of the false positive rate, or 1 minus the false positive rate. So your model, if it's perfect, will have very high sensitivity, which means that it's got a very high true positive rate. Everything along that cross diagonal elements are done very well, which internal would make the specificity 0. So 1 minus specificity would also be 1, and it would fall somewhere here. So if you have a model which has a sensitivity of 1 and a specificity of 0, it would fall here. That would be a perfect model. And of course, there is a trade-off between getting high sensitivity and low specificity, and that's what this ROC curve kind of shows. And we can calculate the area under this ROC curve, and the ROC curve tells us that if it's a perfect classifier, the area under the ROC curve is equal to 1, and if it's an imperfect classifier, the area under the ROC curve, especially if it's just random tossing of coin, if your model is no better than tossing a coin or randomly picking something, it has a probability of 0.5. So a model to be worthwhile should have an area under the curve, greater than 0.5, and the closer it is to 1, the perfect model it is. So that's what this ROC curve does. And one of the things we need for ROC curve are just the probability of y being equal to 1. So again, we did this log project proba like we did here, and we just need to pull out the first column. Remember, that gave us 2 columns, one for 0, probability of 0, and probability of 1. So I need to pull out probability of 1. And then I can write my false positive rate, true positive rate, and actually do a ROC test. So I'm going to run this, and then also run this, which gives me my false positive rate and true positive rate, which are used to run that run those ROCs. And I'm also going to get the area under the curve AUC, and that AUC gives me, and if I go here, gives me a value of 0.72. So remember, this AUC has to be greater than 0.5, so 0.72 is a good number to start with, especially because we are showing data that we have not shown the model. So we can go and make a plot. I want you to kind of go through this. I'm plotting FPR and TPR, and then I'm going to label this as data 1, and then I'm going to use the RUC under 4, and then I'm going to add this as a legend. Okay, and then the location of the legend is going to be in the bottom right, which is 4, and then I show you how to label the x-axis, how to label the y-axis. We add a grid to it, and then the plt.show just shows us the model, shows us the plot. So that's how you come to the RUC. I also give you code which you can follow, and it can be used to plot a confusion matrix, which kind of tells you how many values are where, and one's observed, one's predicted. So this is another way to look at it. But your accuracy, your precision, your recall score are all important summary metrics, and your AUC is another important summary metrics. So if you go back to AUC curve, so you can see the curve kind of gets a kink here, but and another kink, but in general it's a fairly smooth curve that goes up. Again, if I plot this line here, and if my curve were to go in the opposite direction, it would not be a very good model. So for logistic regression models or any other machine learning dichotomous classifier models to do well, they should have this shape and not the other shape, because that will reduce the area. So that is the idea behind the code of performing logistic regression. Again, as I said, part of your example, one of your assignment problems is to perform very similar function, very similar functionality on with the data set that I've given you. You don't have to split that data set into training and testing, because I've already done that for you, and I've also told you which parameters I want as my X or my features, and which one I want as my Y. So a lot of this code can be just reused for that purpose. So I hope you enjoyed watching this video and learning about the logistic regression model that we wrote in the class. I will see you all later. Thank you.